So in GCSE, you learnt that electrons within an atom are arranged in shells, or otherwise known as energy levels. Now, what you learned this year is that these shells can be broken up into smaller parts known as subshells. These subshells can then further be broken down into orbitals, and each orbital contains 2 electrons, and both electrons have opposite spin. Okay, so let's talk about the subshells in a bit more detail. So there's 4 different types of subshells you need to know about. First one is an S subshell. An S subshell is made out of 1 orbital. And if you look here, each orbital contains 2 electrons. So if an S subshell has 1 orbital, it means an S subshell can hold 2 electrons. Next is a P subshell, and that contains 3 orbitals, which means the total number of electrons would be 3 times 2, which is 6 electrons. Next up is a D subshell, which contains 5 orbitals, meaning in total it can hold 10 electrons. And finally, F subshell can hold 7 orbitals, which means it can hold 14 electrons. Now, for the S and the P subshells, you need to know a bit more information about how they look like. So an S subshell has a spherical shape. So in an exam, if they ask you to draw an S subshell, you just need to draw a circle. For a P subshell, it's a bit different. We say it has a dumbbell shape, which looks like this. It's basically like an infinity sign, and that's how you draw it in an exam. Okay, so let's see how these subshells relate to the energy levels or shells. Okay, so in your first energy level or your first shell, you only have an S subshell. So you would call that 1S. So the 1 represents the energy level and the S represents the type of subshell it is. And because it only has 1 S subshell, the total number of electrons it can hold, remember an S subshell can only hold 1 orbital. So that would be 1 times 2, which means it can hold a total number of 2 electrons. In the second energy level, you have an S and a P subshell. And because they're in the second energy level, you call them 2S and 2P subshells. So the total number of electrons in the second energy level would be an S, which is 2, plus a P, remember, can hold 6 electrons from up here. So 2 plus 6, which means it can hold 8 electrons. Now for the third energy level, you have an S, a P, and a D, which makes it 3S, 3P, and 3D. And the total number of electrons that can hold, 2 for the S, 6 for the P, and 10 for the D, so 18 electrons. And the fourth energy level can hold all 4 types of subshells. So that would be 4S, 4P, 4D, and 4F. And if you add all of that up, you get 32 electrons for the fourth energy level. Now all of these subshells can hold a certain number of electrons as shown in this table, but you need to know the order in which these electrons fill up. So from GCSE you learned that electrons fill up from the lowest energy level to the higher energy level. It's the same here with the subshells. It starts filling up from the lowest energy subshell and it works its way upwards. And the order of the subshells goes like this. So most of these are expected. If you look at the table, they go from the lowest and work their way upwards. The only thing that's different here is the 4S and the 3D. So you can see here that 4S comes before the 3D, but you would expect the 3D to come before the 4S because it's in a lower shell. But the reason this happens is because the 4S actually has a lower energy than 3D. So theoretically the 4S gets filled up with electrons before the 3D. So remember this when you're writing your electron configurations because it's a common mistake that people make. So let's look at some examples now. The first one is oxygen. So if you look in the periodic table at the number of electrons it has a mass number of 16 and an atomic number of 8. So 8 tells you there's 8 electrons in an oxygen atom. So starting from the bottom subshell, if we look up, it's 1s. Now this 1s is filled with 2 electrons because there's 8 electrons in total. So the 1s orbital will be fully filled with electrons. So to signify that, we'll put a 2 up here. So that's 1s2. So that shows that that 1s subshell is fully filled with electrons. Next up, we have a 2s subshell. Again, that can only hold 2. And because there's 8 electrons, we've only used 2 electrons. This one is also going to get fully filled. So that would make that 2s2. So we've used 4 electrons from the 8. We've got 4 left. So that's when the 2p comes in. Now, the p orbitals, if you remember, can hold 6 electrons. But we only need 4 electrons. So that means this one's only going to be partially filled. So we would write 2p4 here. So this is one way to show oxygen as an electron configuration. They might also ask you to draw it as a box diagram. So the way this works is you draw one box for every orbital you have. So here we're dealing with 1s, which has 1 orbital, 2s, which has 1 orbital, and then 2p. Remember, p has 3 orbitals, so it has 3 boxes. So the first 1s is fully filled. So to signify that, you draw an arrow to represent an electron. One arrow pointing upwards and one arrow pointing downwards. The reason they have opposite directions is because, remember, electrons in an orbital have opposite spins, so that just shows that. Same with the 2s. Remember, this is 2s2, so it's going to be fully filled. So it's going to look like that. Now for the 2p, the way you fill it up is you add 1 electron to each orbital first before pairing any of the electrons up. So you shouldn't be doing this. 1, 2, 3, 4. Because the electrons are not stable in this format. The electrons always want to stay as far apart as possible, and the repulsion will naturally keep them as far apart as possible. So you will not fill up the electrons with opposite spins together in an orbital when you fill up a subshell. So instead, what you should be doing is filling up the individual spins first. So 1, 2, 3, so they're all as far apart as possible now, and then for the fourth one, you add the fourth electron to the first orbital, like so. Okay, so another thing they could ask you is an ion. So let's look at sodium ion, Na+. So if you look at the periodic table, sodium has 11 electrons. So sodium plus Na plus means it's lost an electron, so it should have 10 electrons. So let's write the electron configuration for that. The 1s is completely filled, the 2s is completely filled, so you're left with 6 electrons now, and your 2p can hold 6. So it's going to be 2p6, it's going to be fully filled. And the box diagram would look like this. So the 2p is completely filled up with 6 electrons. Now, a place where loads of people make quite a few mistakes is when you're dealing with transition metals. Because in transition metals, you have the problem with the 4s and the 3d. So let's look at iron. If you look in the periodic table, iron has 26 electrons. So to write the electron configuration, if we go in the same order as we wrote above, 1s2, 2s2, 2p6, 3s2, 3p6. Next, remember we've got the 4s before the 3d. So we would write 4s2, and then we're left with, so 2 plus 2 plus 6 plus 2 plus 6 plus 2 gives us 20 electrons, so that means we have 6 left. So our 3d would have 6 on it. A shorthand form of writing electron configurations is to simplify this by writing this first part of the electron configuration as a noble gas element. So all of this, if you look carefully at the periodic table, would represent argon. So this would be the electron configuration for argon. So you can just put a square bracket around this to represent all of that, and then just carry on straight from argon, like so. So this is a shorthand form. If they ask you in an exam to write an electron configuration, write the full form unless they actually tell you you can write the shorthand form. Now, what would happen if instead of iron we had Fe3+? So your iron has lost 3 electrons. Now this is important. In transition metals, the electrons get lost from the 4s orbital first. So in transition metals, electrons get lost from the 4s subshell first before your 3d subshell. So that means if you're losing 3 electrons, you'd lose both electrons from the 4s, and then you have 1 more to lose, and that would then get removed from your 3d. So your final configuration would be 1s2, 2s2, 2p6, 3s2, 3p6. Your 4s would have lost both electrons, So that would be 4s0, but you just don't write that. And then your third electron will be removed from your 3d. So that would become 3d5. So remember that with the transition metals, that the electrons get lost from the 4s before they get lost from the 3d.
For more videos like this, summary videos, worked examples and exam tips, subscribe to my channel.